We have Bill Mauchly here today, one of the sons of John Mauchly of Eniac and Univac fame. And I assume most of you know, or at least vaguely familiar with the common story. Eniac was the first general-purpose digital programmable computer, a lot of qualifiers there, not the first computer, but the first computer that led to the modern path where we are today. And John Mauchly was a physics professor at Penn, and his colleague, Pres Eckert, was a recent grad student, I guess, right? And Mauchly was the big idea guy, and Eckert was the implementer engineer. There's a lot. The story of Eniac has been told many, many times by historians and writers, up to about the 70s or 80s, and kind of renewed interest in the 90s. A good book came out. But there's a lot of stories that haven't been told about John Mauchly, including some that are related to Camp Evans here that have never been told about John Mauchly. So we're honored to have Bill with us today, and he'll show some slides, show some artifacts, and tell a whole bunch of great stories. And computer history, we all love to talk about Apple and Altair and IMSI and all great stuff, but it starts with stuff as big as this room. In fact, John's mother was the first computor, literally.
You can't give it all away now.
Right. Bill Mauchly.
Thank you very much, Evan. It's really fun to be here. My father was a big advocate of computer clubs in the 70s, back when things were just starting up and it was a new thing to have your own computer. But he was always ahead of the game because he had always, all his life, he wanted to have his own computer, it seemed like. And that goes back from when he was born in 1907. Unfortunately, that was an era before, when nobody had a computer. Nobody even knew what a computer was. And so what I would hope to do is sort of list all the computers that my father had through his life and his endless quest to get himself something that he could just really call his own and get down and mess with. He was sort of a gadget guy. The story starts, well, this is my father, when he was in his 30s, right? So I'm not, I might figure out how to signal you. Story starts long ago, far away, on a sailing ship, and this is the path of the ship, because the poor ship had no compass. It was an anti-magnetic ship. There was no metal on the ship. It was called the Carnegie, and it was, even the motor was made out of brass. So the reason Carnegie is interesting is because my grandfather, S.J. Mauchly, worked on it. Here he is, fiddling with some kind of gadget. There's gadgets going with the family, I think. And he's, so it was his job to map the Earth's terrestrial magnetism, and they sailed for a decade around all the oceans they could find to see. Because the Earth's magnetic field is actually a little bit different in all different parts of the ocean. So if you're trying to navigate by compass, it matters to you that your compass is going to be off by 5 degrees because the Earth is a little bit quirky there. So my father grew up in this atmosphere of being the son of a scientist, and he always had all kinds of electronic things and magnetic things around him. Well, not electronic things, because it was sort of pre-electronics. The only thing electronic in the 20s were radios. But growing up in the, I guess, the late teens, right? So but he was an electric whiz around his neighborhood, and always had a battery and a light bulb. There was this one story where dry cells back then, were big things that weighed a pound or two. But he always had one of those and a couple wires and a light bulb and stuff. And so they wanted to explore his friend's attic, and so he wired up like a flashlight, basically, just lit up the bulb and was carrying around this contraption as they went up in the attic till his friend's mom found out and was freaked out. She said, "Look at that! That's horrible. That's dangerous. Here, take a candle." So nobody knew too much about electricity, but he made it his business to know as much as he could. He was always wiring up things around the house, and this is sort of a mock title for what really went on here. He loved to read in bed and past his bedtime. His mother was always coming up and climbing up the steps to see whether his bedroom light was on, and then yelling at him and telling him, shut it down, shut it down. And so his answer was, he noticed that there was one step, like the second step on the stairs, that was a little bit creaky, and he could fashion an electric switch under that step. He ran the wires up the stairs, down the hall, into his room, to his little light bulb that he had fashioned in a certain way, so that whenever his mother set on the first step to start coming up, his little light would flash and get the signal and shut down the light. He's in sleep. He's asleep. And then she checked. She goes back down the stairs. The light goes on. Okay, he's back. So he was always filling with contraptions and knew a lot about signaling and stuff, but not so much about electronics. When he went to college, he went into engineering at first, and then into, but he said that was sort of cut and dried, like all the formulas had already been worked out about how engineering was supposed to work. So all the action was in physics, so he got into physics, like his father, I guess, and got interested in terrestrial magnetism and sunspots and a lot of these things. And a lot of the kind of research he wanted to do had to do with statistics, and that's when he first started calculating. So in college, he was dealing with machines like this. This was state of the art here. This was one of his first calculators. It's a desk calculator. And he had a slide rule course before this, but they're not very accurate. This is actually like a digital machine, which was pretty cool in its time. You could type a number in, put it in an accumulator, and then you type another number in, and it would add it to it. And that was the problem. Now you got a number in there. The only way to store it was to copy it out on paper. The whole thing had, and when people did extensive calculations, they were constantly copying things from paper, typing them in, copying it back to the paper, then typing it in again. And so it was labor intensive and also prone to errors, because sometimes you can copy the right number. So he started thinking about this, and he was always, I think it is always the way with gadget guys. When you're using a gadget, you're always thinking about some better way that you could use that gadget, or some better way to do it. You feel like you're wasting your time. If only something. So he started fiddling around. He got his job as he got out of college at our science. He was the physics department. He was the only physics professor there, so he was the whole department. And he taught physics at our science college, which is just over the river in Pennsylvania. And in his spare time, started fiddling around. He was trying to do research, and he was trying to accelerate it. And he was using his desk calculator when he could. Sometimes he would hire students to type things into his desk calculator. And he was working, as I said, on problems to do with sunspots and how sunspots affect the weather, something that's just still in the press. People are still thinking that maybe global warming is just sunspots. Maybe it's not us. But it's still something that we don't quite understand, how sunspots affect the Earth. But it's statistics, and it takes a lot of numbers to crunch it. And I was just saying, the total memory of this thing was not enough to be useful for his plans. So he started, okay. So his idea was to, he had a lot of other interests, I guess, because he was also making other kind of gadgets. He learned to solder, and as I say, he was a big electrical guy, so he was making things. He made these were sort of like special purpose computers, I think. This was a device that you'd enter on some switches, a certain combination, and then you could enter letters, and it would come out other letters, obviously, a cryptographic device. This was harmonic analyzer was another machine he made where you put in the points of a curve, and it would analyze. This was an analog machine actually on the meter, sampled time, but analog voltage, and it would analyze which harmonics were present in that waveform. And, but he really got interested in this counting thing and made his own counter. He was inspired by his friends also in physics down at Swarthmore College, and they were counting cosmic rays. So in cosmic rays, every time a particle hits the sensor, it gives off a pulse, and they wanted to know the rate of pulses, but they were coming too fast to hit in a relay. A relay is a mechanical device that can go maybe 3, 4, 5 times a second, but no faster than that. So what they did was make a divider circuit so that every 2 times this tube changed state, this tube changed state 1 time. So every 8 times this changed state, this tube changed state 4 times, this 2 times, this 1. So you could divide down things that happened really fast in this divider circuit. And these tubes were actually working digitally. They just had on-off states, and they were dividing large rates, like 1 million pulses a second, down into manageable rates that they could count with conventional equipment. So he said, that's great, except you're just counting. Why can't we calculate with using that? It's sort of a simple idea, but it was he was a poor college professor, didn't have the means to buy enough tubes to really do that whole thing himself, and he didn't really understand how you could turn that into a full calculating machine. But he made it his business to learn everything he could about how calculating machines work. He knew how these things work, and that's pretty straightforward. And then he studied, there were other things going on, like Stibitz had generated a complex number multiplier. It was all digital. It was just using relays. And that could go, I don't know, 2 additions a second, something like that. Eniac, he made a machine that could solve simultaneous equations. So Eniac is a famous character in this story because my father was actually giving a talk somewhere, and he was showing off one of his machines. He mentioned his harmonic analyzer. He built a machine, and Eniac came up at the end of the speech and said, that's interesting, I'm building a machine too, and they talked about it, and they became sort of friends, and they were talking, but Eniac said something that really intrigued him. He said, I have digital storage at less than $2 a digit, electronic storage. And a tube at that point costs $3. Or no, I think $2. But it took 2 tubes to make a flip-flop. So he couldn't, for him it was $1, it was $4 a bit at the minimum. So Eniac was saying $2 a bit. He just didn't quite get what he was going at. So Eniac invited him out and said, well, I can't tell you about it because it's a secret, so come out to Iowa to learn about the machine. So he learned about his machine, and he wasn't so interested in that because it was mainly a mechanical machine. It used a motor to keep the digits going, and so it couldn't go fast at all. So all the benefit of being electronic was sort of lost in the fact that it was mechanical. And he was also aware of, so he was constantly looking for ways to do this. So that led him to one of the biggest machines of the time, which was the Bush differential analyzer. Now this calculator is not a very good picture, but lived at the Moore School of Engineering at the University of Pennsylvania. And so my father, in an effort to get close to computing and learn more about electronics, in 1940 took a wartime course, 1941 I think, to learn more about electronics. He took the course at the Moore School. And Moore School at the time was like a center of computing. There was a lot going on there. They were computing for the Army. They had this differential analyzer. There was a lot of electronics going on. They knew about state-of-the-art electronics. And so we studied this machine too and understand how that worked and about the problem they were trying to solve, which is the differential equations that are for artillery tables. So this always gets back to the war, of course. Always gets back to shooting things. And the trajectories of guns at that time, when you made a new cannon, you fired at all the different angles to see how far the bullets would go. That was the way it worked. If you couldn't do that, you could make a table of how far it would go when you fired at all these different angles. But when the war effort was starting up in the early 40s, they were making guns faster than they could make these tables. In fact, they had entire rooms of, I think they were mostly all women, because that's a lot of the men had gone to the war effort, were using these desk calculators and crunching through these equations. And it would take them 2 weeks for one person to get through the equation of one bullet flying through the air and landing somewhere. So it took a lot of people a lot of time to make the detailed calculations. So, and they were also using this. Here's this woman, Kathleen McNulty, who's my mother, operating this machine. She was a math major, just got out of college, said, "My God, there's a job for a math major." And then, who knew? And so she was surprised. And so she was working there, working this differential analyzer. Of course, my father and my mother didn't know each other at that time. But he sort of met her in passing, because he was down here poking around this machine saying, "How does this actually work, and what are you calculating?" And all the methods. He was really interested in the math and that method and stuff like that. So at that point, he proposed. He said, "Wait a minute. Well, I left out a part. He met Eckert." Very important part. Because he was thinking about this for a while, but everyone else he talked to said, "Well, yeah, tubes, but tubes are completely flaky. Anybody who's ever had a radio knows that they're going to, after a half a year, if you have 6 tubes, one of them's going to fail. So if you've had 100 tubes, one's going to fail every day. And if you had 1,000 tubes, one's going to fail every minute or something. So, forget it." So, but Eckert was different. He was this recent grad student and had just finished up the Moore School when he was working on radar work there. And he knew a lot about high-speed electronics, and he knew a lot about reliability. Reliability was one of the big subjects at the Moore School. And he encouraged Mauchly to think that it's not so crazy. If you just use the right engineering practices, you could get a lot of tubes to work. And by the way, this is a pretty cool idea. And so they would brainstorm. Apparently the way they met, when my father was taking this course at the Moore School, and Eckert was actually the teacher of the course. He was the grad student. What do they call it? The grad student who teaches.
TA.
Yeah, the TA. And so the TA soon realized this Mauchly character probably got all his work done really quick and knew what he was doing in basic electronics. And so while everybody else was doing their work, they would sit on the side and talk about these ideas. And then they would keep going. And they were both talkers, and they would keep, and sometimes they would go out to this restaurant nearby, Linton's, and stay up late into the night drinking milkshakes, apparently. Apparently that's the thing to do if you're going to talk about electronics. Just drink milkshakes. Draw on napkins, I guess. I don't know what they were doing. But it probably was a fascinating time, because they started hatching this plan that, yeah, we could do this. And so Mauchly wrote this memo, and you get into a lot of the history books, this part of the story, where he wrote this memo, and he circulated it to everybody in the staff at the Moore School, and everybody thought, yeah, big deal, it's tubes, and some crazy kid thinking this, that's probably not going to happen, got filed away, and was sort of basically lost. And it wasn't until 9 months later that this fellow Goldstein, who was in charge of speeding up the calculations, he was the liaison between the Army and the Moore School, the faculty at the Moore School. He heard about this memo, couldn't find it, so he asked around, and he finally got a copy of it, and he said, "This is good, I want to hear more." And so Eckert-Mauchly put together a proposal for the Eniac. And at this point, Evan had some interesting little sidebar about the funding aspects of the Eniac. Yeah.
Excuse me. Okay, so this is a little sidebar. Let's see where to start. Okay, so young professors at Penn didn't make a large salary. They didn't make a lot of money. And so the U.S. Army Signal Corps had a contract with a lot of universities around the country to do all sorts of research and basically a lot of math. And one of the projects, around 1940 is when the U.S. Army Signal Corps in Fort Monmouth opened this place, Camp Evans. And there were half a dozen or so other sister bases to Fort Monmouth, all working on various things. The biggest technology was radar, cutting edge. And it's very clear today, through historical documents, which camps worked on which technologies. So, this camp was doing parabolic radar research. And they needed someone to compute the math for that. I don't personally understand the math, but that's what they needed to do. That was the task at hand. That project got assigned to the nearest university center working for the Signal Corps, which was Penn. Penn went to the professors and said, okay, who needs some freelance work to make some more money? And that was John Mauchly. As I understand it, that was one of his, if not his first contract aside from teaching there. So, John Mauchly gave an interview to the Smithsonian, I believe, in the 70s, in which he describes a lot of this. And he describes that he went all around campus at Penn. He went to Wharton, to the business school, and gathered up all the mechanical math power he can get his hands on to do this parabolic radar research. And it got to be a real chore, beyond the point of being fun or worth the money after a while. And he said, wait a minute, this is too big a job for mechanical computing. This is a good reason. Maybe we can use that digital idea I had with Eckert. Maybe now this is something we can use it for. So we're not 100% sure, but apparently the story is that he went back to Goldstein and said, look, we can use the digital idea we've been sitting on to solve this Signal Corps stuff. And was told, great idea, but the Army will never fund it. It's too far out. So the proposal talks about ballistics research and trajectories and stuff. And every computer history book ever written since then says Eniac was built to do the trajectories. That's the reason they built it. That's what the funding proposal says. But one of the actual reasons it was done was for the parabolic radar stuff. And I know this because John Mauchly said so in the interview. In the interview in the 70s, which I have, he explicitly tells the interviewer that even he and Eckert have been sitting on this idea for a digital computer, but that every time they got back to the Signal Corps research project, they were, quote, impelled was the word he used, to actually build the computer. So in our museum across the street, we can honestly tell visitors that it's because of what happened here at Camp Evans that John Mauchly stopped just thinking about a digital computer and was inspired to actually start building it. Now, no place did John Mauchly in the interview mention the words Camp Evans, but he did say Army Signal Corps at Fort Monmouth, and he described very clearly which particular problem he was working on. And we know for a fact that only this base did that problem. Therefore, we can deduce it happened here. None of that changes, really, the history, for the computer history side of Eniac. Eniac developed as it would have anyway, but it changes, it's a huge thing for us here at Camp Evans, because that gives us a connection to what happened there. We also have a contract for this place to use the Bush differential analyzer for what happened here for some other work later on.
Yeah.
So that's just a little sidebar that the work Mauchly was doing for this place inspired him to work a little harder on his computer idea.
Mm-hmm. Yeah, I think it's a very important point that from the beginning, Mauchly wanted a general purpose machine. The idea of just making a special purpose machine that solved the differential equations for artillery tables was not interesting. But you immediately saw that there's a lot of mathematical problems. They're all somewhat similar, but they all in detail, they're different. This one you got to multiply, add, subtract, use that number over there, and there's some other order of operations. And so what you really need to have is something that's flexible enough to be a general purpose. And it didn't seem to be that much harder once you got this thing rolling, instead of making it general, making it specific to just do one job, to make it do many jobs. And that was kind of a little bit radical thinking at the day. It wasn't completely radical. I mean, over at Howard Aiken at Harvard was thinking about a general purpose computer that used relays and had a punch tape that told the instructions of what operation to follow next. And that was a decent plan. Zeus, over in Germany, unbeknownst to practically everybody, was working on something that followed a sequence of instructions. Again, following a paper tape. And of course, Turing had already said if you had a machine that had this was in 1937, purely theoretically, he proposed that if you had a machine that had a paper tape and it could do a certain amount of operations, but one of the operations was go to the next place with the paper tape and do what it says there, and then based on what it said there, you could either go forward in the tape or backwards in the tape. If you had that, you could solve any problem in the world, any mathematical problem. Not saying how long it would take, but it would solve it. So this idea of like a general purpose computer was in the air and had been in the air since Babbage, another guy who tried to do this 100 years ago before this, and everybody had forgotten about because it was impractical. So there was this, it was really hard to do, and so it was only people with a lot of money that were even going to try to do that. And the benefits of it, I mean, when they compared how much money you could spend on doing that, and you could speed it up, and you'd spend $1 million to make this machine, and you could speed up your calculations a little bit with these relays that could go maybe 4 cycles a second or something like that. And then you compare that to hiring some women with calculators, and then if you need to, you could hire some more women, and then when you're done, you fire them. It actually was cheaper to hire the women with the calculators. So it wasn't that popular idea economically, but it was in the air. So, so general purpose was good, but the whole point of this memo was get the mechanics out of the way. You gotta go electronic. You gotta not have any mechanical device that has to flip when you're done the instruction, because that's gonna limit how fast you can do these instructions. You can get it down to just same thing that's in a radio. Why can't it go 1,000,000 times a second? It's just electrons moving around. There's nothing that keeps you finishing one instruction, moving on to the next instruction. And as soon as you start thinking about that, you realize, well, suppose I did have to do 1,000 additions, and then I had to do 1,000 multiplications. Well, if it only took me half a second to do the 1,000 additions, and then I had to step in and tell the machine, all right, now we're going to go to multiplications, you've wasted a lot of time, because now it's going to take you 10 seconds to do that. Whereas if you could get the machine to go quickly from this operation to that operation to that operation, with nothing mechanical in between, you're going to be able to solve any problem, and they're just going to go like fast. But you have to make the memory electronic, and you have to make the instructions electronic. You can't just do one, or else you haven't really solved the problem. So that was the idea of the memo. Let's just calculate full bore electronic speeds. So Goldstein was responsible for getting down to the Army. They dragged the guys down there, and they made the proposal. And the Army was like, well, yeah, we blow up tanks. They cost $1 million. Why don't we give these guys some money, and maybe they can, you know, it might work, it might not work. It doesn't really matter. It sounds like a good project, and Goldstein wants the money. So again, because you can read this. There's a lot of interesting details about the Eniac story in this book by Scott McCartney. And no relation to Paul McCartney. And
it's a very good book.
very good book. And it tells, like, one of the stories that's in there is the mice. It was not this kind of mice. The real mice, the real computer mice, were the ones that were going to eat the wires of the Eniac if I didn't watch out. So Eckert, being the consummate engineer, had a cage of unfed mice, and he got a sample of all the different wires that they were considering using, and set them in the cage, and saw which ones the mice sort of favored, and which ones tasted good, and which ones were, for some reason, tasted terrible. And so we picked the terrible tasting wire to go in the Eniac. And that was a sort of a humorous thing that he solved. The big thing that Eckert solved was the reliability issue. The whole reason that everybody said they're crazy was that they were proposing to have well, at first 8,000 tubes. Eventually it turned into 18,000 vacuum tubes, all in the same machine, and it was going to be unreliable. And he said, we can do this. We can figure this out. So the first part of their engineering plan, once they got the money, was to figure out how to make tubes reliable. And they did a lot of research, and they read up what they could. They couldn't find that much. I mean, they went up and talked to Zorkin at RCA, and he said, it's probably not much you can do. You could lower the voltage. That sometimes helps. And that turned out to be a key thing. If you operate them below their maximum voltage, tubes last longer. They also discovered that if they burn them in, the ones that are going to break within the first 10 hours of operation. After that, the ones that survive work for thousands of hours. So that was a good piece of information. And the
statistics ability on that. He was familiar with statistics.
Yes,
right? So
yes.
that was a statistical problem.
A statistical problem, yeah.
Yeah.
So he called it worst case design. I never quite understood what both of the worsts were, but the ideas with the circuits that they were making was they were buying things like resistors that were supposed to be good within 10%. And then you buy another resistor that's supposed to be good within 10%. And if you try to use them together, well, the worst case is this one is 10% bigger than it should be, and this one's 10% smaller than it should be. So the tube is going to be operating in a different voltage than much different voltage. So now you stack those up against each other, and you got to make a circuit where that doesn't matter. So the idea of working digital, where everything's on or off, was a good idea. Because as soon as you try to hedge your bets and try to use analog voltages and say this voltage is slightly more than this one, and that's going to make this happen, that's when things started to fall apart. So the first proof of concept that they made was to make two accumulators. Their architecture was loosely based on this thing. I think that was sort of, again, Mauchly's inspiration. He said, these things are great. If you add and then you hold the number in there. And the problem is now you want it to add it to some other number, so you have to have another accumulator someplace else. Send that number over to this other calculator. So imagine if you had 20 desk calculators and they're all hooked to each other by some magic interface. So this guy could send a number to that guy, and then when he's calculating, he could send it to that guy. So that was the basic thing. So they made two of these accumulators, and they hooked them together. And at this point, they were, it was like in the middle of the night, I think, that they finally got this thing to work, the first ones. And there was nobody much around the Moore School, but the differential analyzer, which was in the basement, they operated 24 hours a day. So they ran down there, and there were some women who were turning some equations, and my mother was one of them, actually. They said, you got to come up and see this. Well, they didn't know what they were going to see because the project was top secret. They were in this closed room, so they got to go into this closed room, and as my mother would tell the story, that they saw these kind of crazy guys who had been up all night, and they had this big machine, and they said, now look, see, we put 5 into this accumulator over here. See, it says 5, and it has lights lit up 5. See, and then over on this machine, it said 0, right? And now when we press this, it adds 5 1,000 times. And look, there's the answer, 5,000. Never like. Use all this to multiply 5 times 1,000. You guys better get a light. So they didn't quite get the idea that it could do that, but it could do something else as well. Yeah. So that was the damn thing woke up. So when finally the Eniac, when they were finally finished, they made 20 of those accumulators, and that accounted for the 20 words of memory that the thing had, and operated at 5 kilohertz. So this was a big improvement. Mainly that number was a big improvement over anything in the world. So I have some pictures here to show the lovely monster. Took up a whole room, and it was filled with these patch cables. And so these are the individual accumulators here. Not all the accumulators just added. There were some units that there was a multiplier, there was a divider, a square rooter. And these things are function tables, what we would call today ROM. You would set the numbers in here, and these dials, they're little rotary switches. digitally. And then it was addressable. So if you said, give me the number that's in slot 3, it would spit back some 10-digit number. So that was read-only memory. And at the time, probably the largest read-only memory in the world. There were hundreds. I don't know what the exact number of hundreds of words of read-only memory there were. So there's a couple more pictures here. This is a close-up of an accumulator. These, I don't read these. These are A1, A2, A3. So these are some of the switches that you can set on the front. So the way this thing worked is a number would go into an accumulator, and then it would add or subtract to the contents of that accumulator. And then this accumulator would send out a pulse. And that pulse would be to some other unit, one of the other units, to say, you're next. I'm done my operation, you're next. So they would sort of do a daisy chain kind of operation, and that's the way programming worked. Go ahead. But the real programmable part was that these trays along the bottom, which were connected by patch cord. So these are like buses that we have today. So if you want to get a number from this machine, you say, I'm going to send the number into the tray 1, and tray 1 goes all the way down across the whole machine, and then over here you take the number out of tray 1 and put it into this accumulator. Go ahead. These are women accumulating.
Were they using technology like in the old IBM calculator machines? You put, the program was a physically wired thing you'd slide in. And,
No, it was, well, it's that idea that the program was a set of wires.
right, and you'd slide it into the machine, and that machine would then use that program. You'd pull it out and slide it in another panel.
So that's a quick change program.
Yeah.
This was before, this was probably the reason that was invented,
Yeah.
was because this was not a quick change program. They would run a program, and some of the things they ran took days or more, weeks. But when they had to change the program, to physically change the program took a couple days because they had to change all these wires and stuff.
So this preceded those.
I might have missed this part when you said the memory was 20 words. Is that what you said?
Yeah,
How large was the word?
10 decimal digits.
10 decimal digits, which would be how many? Oh, it
About
was,
4 bytes.
Oh, it was analog. Oh,
No, not analog,
It was
but it was decimal.
It was decimal.
Yeah.
It was decimal, not binary.
Yeah.
Okay.
So it could represent a number up to 1,000,000. So that's it's about really 3 bytes of memory.
Did they use binary coded decimal or did they use just binary straight?
Yeah, is it straight binary or binary
BCD.
decimal?
It would be binary coded decimal, I guess.
Okay, so
Yeah.
that would be like
So
4
three-
bits per word.
3
Yes.
bits
Okay,
per.
great, thanks.
So these machines had those panels in
think.
effect. As a stationary part of the machine, each accumulator was dedicated to one task.
Yes.
And the IBM thing, you slid in the panel and pulled it out, was a next development on from that.
Yes.
Oh, okay.
So, yeah. So that's a good point. Here is Eniac, the man, standing in front of his baby, pretending he's operating it. Sure, he's just posing, but I don't think they programmed in a suit and tie, but I could be wrong. So here's the floor plan. This thing was like 30 feet by 15 feet, weighed 30 tons. I said it had 18,000 vacuum tubes, 150 kilowatts.
I have a question. Is that there was heat a problem with
Big
it?
problem. Had a custom designed air conditioner. I don't know if you can see that in some of these.
Ceiling in
Yeah,
the previous picture.
yeah, yeah. They had a big air conditioner because these, tubes are hot. I mean, they make a lot of bread. So here's so there's function table panels, there's accumulator panels. You probably can't read these, but there's a bunch of accumulators and multipliers. So this was the idea. The trays run around the outer perimeter of the room, and they're the buses. And then each accumulator can plug into a bus and send its memory to another bus. And then there's an important thing called the master programmer, which control a lot of the looping and other master control.
This is a more esoteric question.
Yeah.
I imagine you came on the scene a good bit later.
Yeah.
But were you ever in the presence of this equipment?
Well, that's a good question. That's a good question. The Eniac operated for 10 years, and then they were done. There was more advanced computers, so they said, let's break it up. It's huge. Let's get rid of it. So they scrapped some of it, and some of it went to different places. Some was saved. Smithsonian now has a couple panels. The Moore School,
Silicon-
Pennsylvania,
the
still has a
Computer
couple.
Museum in Silicon Valley has.
There's a one panel in Silicon Valley. There's,
So it was scrapped before you were born then?
yes.
So only a small percentage of it survives today.
I'd say in total about half.
Really?
Yeah.
Is-
So this is one of my life's quests here, is to get the Eniac back together, which
oh,
obviously,
no one has actually reconstructed it, you're saying.
right.
The only thing that's been done is, I think some students made an FPGA.
Yes, the function of it has
Yeah.
been repeated in electronics
Yeah.
and software.
Well,
Which is
basically,
interesting.
these diagrams are this is miniaturized for our present day computers to overgeneralize,
Yeah,
except our diagrams don't show the little people walking around.
that's right. But I still think of it that way. I think, okay, I'm going to load the accumulator with a number, and then I'm going to multiply it. And if I can keep it all in the registers and not have to go out to main memory, that's going to save time. I'm a DSP programmer, and the architecture of DSP processors is not that different from the accumulators. It's fairly different from a general purpose computer today, because it's sort of a parallel processor. There's multiple units, and the main computer architecture that most people are familiar with is more serial. But now it's sort of coming back on that side of the being a parallel machine, because we can't get the serial machines to go any faster. So we said, well, what if we had many parallel machines? I'm not sure if I have a couple more slides there. Here's somebody with the job of replacing tubes, and which was a full-time job. They did have programs that you could run to tell them which tubes were bad, which I thought was pretty clever. And I think this is another one of the engineers, Harry Husky, and with throwing the switch or something, doing something important. Okay.
How many vacuum tubes did it take to constitute 1 bit?
Yeah. Well, it was. I think the general answer is 2.
Okay.
The way they store the numbers, I rethought it. It's not binary coded decimal, really. It was what they called a ring counter. So they had a state machine that had 10 states.
Oh,
So it would always be in one of the states, and that represented a digit, a decimal digit.
Oh, so the hot bit would represent the value, right?
Yeah.
So it'd be 10 bits for 10
Yes.
decimal.
So that took 20 tubes.
Okay.
So one of these, one full rack thing held 20 tubes and could represent 1 decimal digit.
That's amazing.
And so when you put 10 of them, you get the 10 decimal digits that took up the
If I
whole
could
thing.
say, Ron,
Talking about ring count.
Later today, if you come over into our museum exhibit, we have a half adder, which the person who gave it to us pulled it from Eniac, but it says Remington Rand on the side. So we know it was Univac.
Probably.
It's a Univac part. But it's the same idea. We have one of those. We have one of these rows of a Univac. And it's the same basic technology
Yeah.
a few years later.
Yeah, well, they used it right until the 60s. Yeah.
Guard here wanted to reassemble an Eniac.
Yeah.
You have a problem that components are no longer available.
Yeah. It's not so important to me that it be fully working. Because as I say, 150 kilowatts, it's not ecologically sound idea to keep something like that on, just for demonstration. Yes.
Was there any marginal checking used in this system to find tubes that were on the verge of failing?
On the verge of failing.
Yeah.
I-
Like
I-
running tests with,
I
you know,
think they would
voltage and over voltage?
They tried not to turn it off because that's bad for tubes. But there were power saving measures taken in some parts of its life. As I say, it operated for 10 years. And they would turn it off, and then when they had to turn it on, they would run these diagnostic programs. And that would try to sort out the ones that were going to fail, because that's usually when they would fail, is like in the first hour of operation after they were turned on.
Did they duplicate some functions to improve reliability, let's say using 2 tubes instead of 1?
Not in this machine, but in the next machine they made, they actually did that. They made 2 computers side by side.
I would assume behind here someplace you have a power room and an air conditioning room that are almost as big as this. I don't see anything.
There's
that really
some of
looks
these
like-
panels are power supplies,
Are
so
they?
they don't look big enough to do the whole
Yeah,
thing.
it looks like you physically need to.
But the air conditioning unit here, you can see up here, there's extensive ductwork sucking air out of every one of these panels.
I heard that one of the diagnostics was to turn off all of the lights and to look for filaments that weren't there. Is that?
I never heard
did
that.
Actually,
I never
that's,
heard that.
that's a
Yeah.
diagnostic.
That sounds like a good idea.
There were also some urban stories. Like there was an urban story that when they ran it, the lights in Philadelphia dimmed for a while. Yeah, it's a good good story, but it probably never happened.
Right.
Yeah. Just in the block, not the whole city.
Right.
Yeah, I guess we should move on here. I've wasted a lot of time here. Okay, so this was great. My father said, wow, I finally have a personal computer. And then they said, okay, we're going to move it to Aberdeen. They took it apart and took it away from him. He said, why? Wait, my computer. So it was, but even while it was being designed, they were already having better ideas about better ways to do it. And of course, they had to freeze the design because they wanted to build it. So they said, we'll design another computer. If you have new ideas, we'll put them in the next computer. So they started building this next computer called EDVAC. And they got a contract for that. And the big new idea there was this plugging the cables thing is for the birds. We got to get a big enough memory that we could put the program in the memory. And I've heard them say that that seemed like an obvious idea. You got to get the program in memory. But since then, that idea of putting the program in memory is called the von Neumann concept, the stored program concept. But it's actually a little bit more than just putting the program in memory. What happened was they were halfway through designing this big wig, famous mathematician, von Neumann, the most famous mathematician in the world at the time, found out about it. And there's stories about the interesting way he found out about it. But he came and joined the program, and he was interested in all kinds of things, computing, and a certified genius. And so he contributed to the meetings, and they were all sort of brainstorming on how to make this next computer. And he said, well, can I go, I'm going to write this up in a little paper describing our ideas. And next thing you know, the other guy, Goldstein, sends this paper out as an unclassified document to 30 or 40 of his closest friends. Or not his friends, but a lot of von Neumann's associates, the scientific bigwigs at the time. And so all of a sudden everybody was like, this is great. Of course, stored programs, electronics, we should do this. So von Neumann got a lot of the credit for that, and he never actually fessed up and said, yeah, you're right. So we think Goldstein and von Neumann were sort of complicit in that. And von Neumann was sort of famous for that, taking credit for whatever he could in his realm. So, but that wasn't the beginning. That wasn't the end of the bad news. Also, some different people got in place, and the Moore School decided to change their policy, and the Eckert-Mauchly would have to sign over all the intellectual rights to the school. And the agreement before then would be that if they wanted patents, they had to pay for them themselves, and they could keep them if they wanted. That's fine. But it was sort of like but once they found out that the computer was a pretty valuable thing, then they were making another one. They said, we went in on this, understandably. But the result was that instead, Eckert-Mauchly said, "Can't we stay?" And they said, "No, not unless you sign over your patents." And so they said, well, "Then we're leaving." So they were sort of stuck without a job, and without their computer, they had to abandon EDVAC too. And the idea is, because of this publication, the EDVAC ideas became public domain. So all of a sudden, they lost a little of their lead. So go ahead. So they're out on their own, but they had plenty of friends. This is my father, John Mauchly, with, well, it turns out it's the programmers of Eniac. Here's my mother again. They're still not married, but they know each other. And it isn't long before she gets assigned to Aberdeen to be a programmer for the Eniac. They took the women who had started out calculating the artillery tables and taught them how to program the Eniac. They sort of taught them. She said they really had to figure it out themselves. They gave them the blueprints. But anyway, so she was an Eniac programmer at that point, and she was down with the computer, and Mauchly would go down and visit the computer, and he would also talk to Kathleen Mauchly. And then later, Mauchly would go down and visit the computer and Kathleen Mauchly and Kathleen McNulty, and then later he was going down to visit Kathleen and not so much the computer. So, so then they got married, and go ahead. But they were still out on their own now, so they decided to start their own computer company. So they called it the Eckert-Mauchly Computer Corporation, and this is on the building, not the first building they had, but the one they ended up with on Ridge Avenue, where the UNIVAC was built. Their business plan went, this piece of paper, which is 10 mimeograph pages, went up for auction a couple of years ago and was sold for $75,000, which is beautiful. It's outlined on a plan for the development of electronic computers. And they say, we're going to start this company and we're going to make computers, and they're going to be used in industry and industrial control and scientific and business and all kinds of things. They even, and they were very prescient. They actually hit on the nail on the head of the way computers were going to be used for the next 50 years, for the most part.
The good news,
No
if
iPod.
if I remember correctly, Mitch Kapoor of Lotus fame bought the document and was working out a deal to load it to the Computer History Museum in Silicon Valley. So it's not in private hands, it's some rich guy's library.
Yes, that's true, yeah. So they started this company. It was the first computer startup. I don't know if you can see that very well. It's kind of dark. But it was a big, empty warehouse. This is a picture at the Ridge Avenue facility. Go ahead. And here's the inside with some people working. My father was an avid photographer. As I say, he was a gadget freak. He always had a lot of cameras around. He had not just regular cameras. He had like a stereo camera and an SLR camera, and he had movie cameras. He always liked all that. Anything with memory in it, he was interested. So these are some guys. I don't know who these guys are, building computers. So the first computer they built was the Binac. He asked about redundant systems. The Binac was a computer that had two identical memories and two identical computers, and they ran in tandem, and they checked each other. So if there was ever an error, they would stop and say, "Whoa, hold on." So this was the first stored program computer that they built, because they had plans for the EDVAC, and it's very EDVAC-like. And used the main memory is a Mercury delay line.
What did Binac stand for?
Probably binary automatic computer. Yeah. I think that's right. Yeah.
What do they use the microphone for?
You see a microphone?
Yeah. Sure. Elvis Presley.
Yeah. That's a good question. It's
Make announcements. with
possibly there was a
25
demonstration or something there. I'm not sure. Yeah, this could have been taken at some announcement.
So these were improvement on EDVAC or Eniac?
So the big improvement over Eniac was the stored program, and it had a huge memory.
Is that
Two,
scope back there, the same
2,000.
scope that's in the corner of the room over here?
just about.
I think it's a 511, not a 512.
But that's,
Yes, that is the scope.
Look at that, that's funny.
Also.
It's pretty close.
Well, this
yeah.
one up here is actually the proper vintage.
Which one?
It's a non-plug-in scope.
Oh, this one.
Yeah.
It's pretty close.
40, late
1948 for
late
that one.
1948.
Bill, if you look
One prior
at
one.
the knob layout, it's pretty darn similar.
Wow.
The front panel is pretty similar to what's in the pictures.
Yeah, since this is a lower speed scope, that's probably 511, which was a 10 megahertz scope, or 8.
Steve knows
Oh,
scopes.
that's on the side.
Oh,
There's a lot of air conditioning going on here, as you can see.
The fans too.
This is air conditioning. It was a non-air conditioned building, however, much to the consternation of these guys, who were forced to, asked to work extraordinary hours and 7 days a week. The more they ran out of money, the harder Eckert tried to work them. And yet, it was supposed to be terrific. I mean, electric, the amount of energy and ideas that were coming out of those things. Eckert once said, we were inventing something new every day. And so a lot got done in this period. This is built in the 48 and ran its first programs in early 49. Neck and neck with the guys who, in England, who had read the EDVAC proposal, the one that von Neumann wrote, and said, this is a good idea, we can build one of these. And they built one in Manchester, England, which was the first stored program that was actually operational. But it was a baby machine, not intended for production. Here's Mauchly at his desk, at the time, in his office. And here's some other people working hard. Actually, they're playing cards in front of a large computer. Another shot of, could be the Binac, or could be the Univac. Now, the thing that Eckert was really hot on was the Univac. The Binac was sort of a stopgap measure, but the Univac was their masterpiece. It was intended to be the mass-produced computer, and it was going to have a digital tape. Unfortunately, that didn't really exist at the time, so they had to invent. They actually created the formulation for this metal tape, and created the tape machine to play it, so that it had. They had these high-speed magnetic tape units, and I don't know who that guy is either, but he's working hard. That's good. So these guys, more scopes in the background. So the result was this beautiful machine, the Univac, first business computer. So these tape machines in the back. So it's most famous for its prediction of the 1952 election. As sort of a publicity stunt, they wrote a program based on early poll results and statistics. They predicted the election. And NBC had it. It was showing on TV, and they were making a big deal out of it. And like at 7 o'clock at night, with 2% of the vote in, I'm not sure about these numbers now, but it predicted a landslide for Eisenhower. And everybody was like, what? It's supposed to be a close race. That's ridiculous. There's something wrong with that. And so they said, are you sure about that? Why don't you go back and check that program? So they said, the program's right, but we'll fudge it a little. So they adjusted some constants in the program so that it predicted, and they announced that it was going to be a slight victory for Eisenhower. And then at the end of the night, it was a landslide for Eisenhower. And they actually came on the air and told about their little farce. Go ahead. Here's another picture of the Univac. So, go ahead.
Pause.
It was a cool machine. You could walk inside it. What could be cooler than that?
So this was Univac, how was that related to their computer corporation?
So this was the second product from the Eckert-Mauchly Computer Corporation.
What's the Univac?
It was Univac, yes.
So Univac Corporation is the successor. Or was
Yeah.
the successor?
Well, the sad story, the long story, it seems like this is long enough, don't you think? But the long story in here is that they were not doing too well, and they were not businessmen, and their company was doing really badly, and they had a lot of bad luck to boot. The main thing they did was underbid the computer, so they were selling these things for $100,000, and it was costing them $200,000 to make. So that was sort of, you could tell that was going in the wrong direction. Subprime mortgage rate. But they got an investor, Harry Strauss, put in $500,000 to keep him alive, and they were doing okay. Then my father got blacklisted by it was the McCarthy era, and because somebody had found his car parked down the block from a communist rally, they decided that he was a communist too. And so he wasn't allowed to come to work for a while. Wasn't allowed in the building. But the real problem was that this Harry Strauss died in a plane crash, and so the rest of his company, his investors said, we want our $500,000 back. You can't have that investment. And so they had to sell quickly. So they sold to Remington Rand, which was a big company at the time, a competitor to IBM, but not as famous. They sold out, and so Remington Rand picked up the pieces and started making Univac. So they became the Univac division of Remington Rand. And unfortunately, we can go on to the next slide, they also...
Did they preserve the name though, right?
They-
Univac is
yes.
still-
Yes.
Remington merged with Sperry, which became the modern Unisys, which is still around today.
Yes. So that company's still around.
How did IBM manage to muscle its way in and take over everything?
They were better at business.
No, they used
They
their
were-
old-
they were much bigger.
Microsoft of hardware at the time.
They used their old card punch machines to find profits from that, to finance competition whereby they undersold at a loss their own computers, which they didn't sell them, though, they rented them out.
Mhm.
And you couldn't resist the deal because the whole thing cost less. If you got
Yeah.
if you used an IBM computer, the key punch and then
Yeah.
the whole setup was cheaper. And so you just used that to, use their
I
market
work
power.
for Cisco now, and it's amazing how much power you have in the market when you sell a broad line of products.
Yeah,
And you just say, well, you want the best, right? And you want us to take care of it. You don't want it to break, and you want us to be around in 10 years, and you want.
Yeah.
And there's a lot of good reasons for going with the big leader.
yeah,
And if you want all this stuff to work together, well, you better get it all Cisco's.
yeah.
Yeah.
Couple of things,
Yeah.
all the equipment, like the tape drives, had this really wonderful curve to them. Just wondering if there was actually someone designing the look of that, or was it just a coincidence they felt like it? Yeah, because it's a hard,
It's not that easy. Yeah. I don't know. I don't know that question.
because everything IBM did was boxes.
Yes.
Most things are boxes, and this has curves in it, and it just like that's harder to do. And
You're right.
So,
Yeah, look at that.
Certainly prettier.
It's
I mean,
pretty.
I'm just thinking,
And
unless they
she's
had-
not bad either, you know.
Yeah, so about Kirk. But it's like, unless they had Raymond Loewy or someone so by, I'm not sure what,
Yeah.
it was, just part of it is, at that age, everything was streamlined anyway.
What I'd like to know, it makes sense, because I remember seeing the IBM drives where you had a window and it moves up and down.
Yeah.
How do you open that? I mean,
They
I can
flip
see
over
they're
the
open,
phone.
but they're shutters?
Yeah, I saw a picture, they hinge open.
Okay.
Really.
Mhm.
Now, okay, the other thing is, I don't see any punch cards anywhere.
Yeah, that was a mistake they made. See, the world was all punch cards, and they came out with this tape machine. They said all I/O is going to be a tape machine. You can just type it in here, and it goes onto the tape. And
So IBM
they had to scramble
so
to make a
IBM's
card to tape machine because they realized as soon as they brought it
so
out that the market
IBM's
wanted that.
leverage was the punch card.
Yes,
That
yeah,
was
that had been
what
established
sort of
for
got them into
2
the
decades.
business end of things.
Yes,
Nice.
people were using punch cards for probably longer than that. How much time we have?
Probably
Then?
just to its day.
Till about 1:15, I have a couple announcements to make as well.
Okay. All right. So the bad part about getting bought was there was a big company and they separated Eckert-Mauchly. And so he was interested in the software and he was put in the software division. And they did some great stuff and made compilers and was researching the applications. Eckert-Mauchly stayed on and continued to make Eckert stayed on and continued to make computers with Remington for a number of decades. But Remington Rand didn't recognize the importance of software, and they basically killed his software group and said, you can report to sales group in New York, and maybe they can find a use for it. So he got pissed off and started his own company. And this was in 1960. So at this point, he decided, if I'm going to have a computer, I may as well just buy it, because it's too much trouble to make these things up. And now that there's more than one in the world. Yes?
Would you comment a little bit on your attitude and your father's attitude in the 70s,
Yes.
during the rebellious generation?
Okay. I'm going chronologically, so we'll get there in just a minute or 5. So the next thing he does is start this company called Mauchly Associates. And I just heard this story last week. Apparently they were starting to make money. They were doing scheduling and critical path scheduling, or the construction scheduling. And they had about $40,000 in the bank. And Rocky Martino, who was head of sales, said, you know, let's keep that in there. We need that for payroll, but I have to go to Europe for a sales call, so don't do anything with it. So when he got back, he found out that my father had bought a computer. He couldn't live without a computer, I guess. So what he bought was, then I had never known this, I'd never even heard of it, the All-Whack 3E, which is this little company that only existed for about 3 years.
We're all laughing about the 3E.
Yes, 3E. Yeah. I think they used a capital E, but I threw it at small e. Tube computer, whopping 8K of memory, and apparently comes with an oscilloscope. But I'm not sure. This was an era when computers still had oscilloscopes with them. Maybe that's a data output device.
Teletype.
Yeah,
Wow.
and a teletype.
Terminal.
Yeah. So that was pretty cool, but you couldn't.
Forbidden planet.
But then he crossed over to the dark side. The IBM 1620. So he completely divorced himself from IBM, from Remington Rand, and said, "All right, I'm just going to get the best computer I can get for the money." And that turned out to be this baby, which was a 1620. And then, go back for a second, because there's just one thing that happened. This is where I come in. All right, so now I'm 7. All right. And so he brings the family in some evenings, because he really likes, back to the idea that he wants a personal computer. He would go in, they would use the computer all day, and then he would go in at night and use the computer all night, because he had it to himself. Everybody wants the computer to themselves.
This
This
is
is
your
something.
first personal computer.
So that was his. He said, "Finally, I have a personal computer I can use." So he would bring the kids in, and we would play blackjack and games and stuff on the computer while he was screwing around with something else, or teach us how to. He even tried to teach us assembly language programming in this thing, which that was a mistake. So this was a wacky little computer. I think it had 40K of memory. 40K, we're getting up there.
Oh, I have some of the core from one of those in the other.
Really? Yeah, it used core memory, magnetic core memory.
It was.
And it was solid state, no
a
tubes.
binary. It was a decimal machine, by the way.
And it was a decimal machine, right? It stored it in variable length decimal numbers. So,
When did they make true binary computers?
well,
When did they start actually doing that?
they were already, everybody,
Oh, really?
Yeah, they did switch.
they went back and forth. Like the English computers, the Manchester Baby and those guys, they went to binary right away. Eckert-Mauchly said that the reason that even the Eniac wasn't binary, I mean, everybody knew about binary. It's not like somebody invented binary. And it's a more efficient way to represent numbers. But the Eniac used punch cards. So they knew the I.O. was going to be base 10 on these punch cards. They said, now if we start base 10, and then we have all these converter circuits that convert it to base 2, and then now we're going to have more buses because we're sending these buses around the room. And they decided it was going to be more expensive to take more hardware to actually go to true decimal. So they said, let's keep it decimal.
Right.
Yeah. So this little device, which we didn't bring in from the car, my father was a big Heathkit advocate, built a lot of kits. He had all kinds of things around the house. And one of them was this analog computer, which is not really a computer exactly, in my definition of the word, but they call it that. It had a bunch of resistors, capacitors, and sort of initiators that you could put in different circuits. So it's more like a really advanced breadboard that you could put together circuits on. It was used in conjunction with a oscilloscope, and I remember him showing me how he had simulated a bouncing ball curve. So somehow he had made this sort of complicated oscilloscope trace that had showed the path of a bouncing ball.
Well, it had integrators, so it could do
Integrators.
differential equations. A
Okay.
bouncing ball is a second order differential.
Okay, that's it. Had integrators. Did it have differentiators? I guess.
Could have.
So based sort of on that idea, he was still liking this idea of like a portable computer. So I said, yes, cool. I can make it. He could make the first suitcase model computer. So he, as I say, they were working on this scheduling problem. You know, how to do construction scheduling. And they call it critical path method, CPM. And so they said, the big computer's great, but it wouldn't be great if we had like a demonstrator or something you could take out in the field. You could enter your numbers in here, and it would spit out, you know, what's the most critical path. And so Evan was the one that sort of got us re-excited about looking into this thing. Was this the first suitcase computer or what? So we did some research down at Penn to find more about it.
I'll be very
Yeah,
quick.
go ahead.
About 18 months ago, I'm writing a computer history book, and 18 months ago I got interested in this. So I went down to Penn to the Mauchly archives and found very little information. So I spent 18 months studying it, found more information, and I contacted the Mauchly family, and they said, okay, Bill's the family liaison to historians. So I brought him back to the Penn Mauchly archives with me. Now that we know what we were looking for, we dug through the archives again and found all this new information that's really never ever been published before. So that's the chapter in my book coming up, a little commercial plug.
Great, yeah. There was some question about how many they ever made, and we can't find this one. So there probably weren't very many.
Very few.
Trouble was it was not a general purpose computer. It only did this problem. So it's back to a special purpose.
Was it all solid state?
No, it was op-amps. It was analog.
Yeah, solid state.
But solid state analog.
Yeah.
Yeah.
Solid state, not tube.
Not tubes.
Right.
yes.
Right.
At which point did you switch from tubes to transistors?
So it seemed like right around 1960. So that
My wife worked on the first transistorized digital computer.
Oh, really?
Transistorized.
Gene Felker at Bell Labs, and it did much what Eniac did. You could do addition, subtraction, multiplication, and that was about it. There was no logic, no conditional logic built in. But if you could, I figured out a way to do it, and we did actual radar work on that computer.
good work.
Which computer was that?
What was the name of that computer? That was
Tried.
Oh,
Tragic.
Tragic, yes. Tragic
Right.
is.
I don't think there ever was a second one. I don't know. I think it was a one-shot thing.
Yeah.
It was Gene Felker who was VP. Later on, he was VP at Bell Labs.
Mhm.
Very interesting.
Yeah, but that's fairly Google.
Yeah. So finally, computers got cheap enough that Dad said, I can put one in my house. The one he chose was a Data General Nova 1200, which he purchased used, which with all the gadgets, I think ended up being $30,000. Pretty expensive for the day. And because he went for the disk drives, you know, the hard disk drives that were this big and held 1 megabyte, and got the extra memory, packed it out all the way to 64 kilobytes, and 16K of memory took one of the 14 by 14 cards in that machine, so that was four card slots. And we had this in our house, and it made a lot of noise, and we had a special room built for it. I mean, he was always thinking ahead. When we had a little bit of money, right at the end of Mauchly Associates, he sold the company in a stock swap. And the stock promptly went to zero. So, but for a brief period of time, we had some money, and my father renovated part of the house and made an office for himself. And he went to the trouble of making a reinforced floor for the computer room, because he figured, computers are heavy. You gotta put something decent in there. So we got this machine. This is just a picture of the CPU. He had a line printer and a terminal and stuff like that. So unfortunately, '73 was a bad year for fans of the Eniac. And this is also a long story, and a big part of the story that's in here is the Remington Rand was abusing the patent for the computer that they had bought when they bought Eckert and Mauchly. They did a stock swap, not stock swap, a patent swap with IBM. They traded the patent for the computer for the patent for the punch cards. Good deal, actually. So IBM wasn't paying any royalties, but they asked of all the other computer companies to pay extravagant royalties in the tens of millions of dollars. So they said, the heck with this, we'll just invalidate the patent. So they set their lawyers on it, and there was a big patent case in 1973, Honeywell versus Remington Rand, in which, among other things, they tried to, it was an antitrust case, but there was also this Eniac patent case. And it turned out the Eniac patent was invalid for a number of reasons. One of the main reasons was that von Neumann had published this paper describing all these computer ideas, and that was in circulation more than a year before they filed the patent. So once again, they had been screwed by von Neumann, but it is, the more damaging part was this, from Mauchly's point of view, was the thing with Adanasoff. They dug up this computer that Adanasoff made, machine, I should say, and convinced the judge that it was prior art for the computer and that the patent should be valid because Adanasoff made the first computer. And they had proof that Mauchly had gone and visited Adanasoff and learned all about this machine before he ever started working on the Eniac. And so if that was a computer and Eniac and Mauchly knew all about it, then he must have stolen the ideas from it. And that was about how deep the judge understood electronics, which was not at all. And so ended up ruling in favor of Adanasoff and actually saying in his judgment that Adanasoff was the true inventor of the computer. Who? What? What's he talking about? The Eniac, and specifically the Eniac patent, has very, very little to do with the ABC machine. Nothing. You can't point to anything in the ABC machine and then say, and look, here it is in the Eniac. There's nothing there. The ABC. I think I have another slide that goes into this a little bit more. But the thing was abandoned and torn apart. Nobody cared about it until the trial, and they said, "Oh, this was a great thing. I can't believe we missed this." And then, so Iowa went crazy and said, "Oh my God, we invented the computer? I had no idea that anything technological ever happened in Iowa." And so the whole state of Iowa decided they were going to champion this idea that Adanasoff was their man. And so they funded millions of dollars of work into publicizing this, and they funded a book of bad-mouthing Mauchly and telling a long story of the wronged inventor. And they also funded the recreation of this machine for $500,000. And sure enough, it doesn't work. No, it actually does what it was intended to do mostly. Like Adanasoff, they had problems with the punch card systems, which he had tried to invent. He tried to reinvent the punch cards for some reason and failed. So he never had his machine working to a point where it could ever solve a problem. So it never actually solved the real problem. But now they found some workarounds and they fixed that. and they got it to do what it was supposed to do. So the trouble is, what it was supposed to do was very little. It was not solving the interesting problem. I think the demanding problem that the Eniac solved was how do you compute electronically, and that problem is broken down into how do you store the numbers electronically with no moving parts, and then how do you keep the operations going with no moving parts, and then how do you go on to the next instruction with no moving parts. You got to have the whole thing with no moving parts. That was the interesting problem. None of that happened here. He had a machine that you turn, every time this thing went around, it subtracted a bunch of numbers from a bunch of other numbers that were on another drum that was turning around. That's all it did. You turn it, it goes around again, it subtracts again, it subtracts again. It just keeps on subtracting until one of them goes through zero, one of them becomes negative, and then you're supposed to stop, push a button, convert those numbers to decimal, punch them out, or no, I guess it didn't convert them to decimal. Just punch them out on the punch cards, and then do a little stack of cards. And then you sort through the cards and pick a different set of cards, and you put those into the hopper, and you read those in, and then you subtract again. So to do this little thing of just solving these equations, it took an operator sitting at a desk for days to get it to work. So it wasn't general purpose. It couldn't solve any problem. It was meant to solve one problem with the help of a human. So it didn't do the key thing that computers do. There was no sequence of instructions. So for anybody to say, to even call that a computer, you're really generalizing the definition of computer to a point where it's sort of meaningless. You're just saying something that computes. Well, this is something that computes too. So is that a computer? Did he invent the computer? You know, it's not that simple. What we call a computer today is something that follows a sequence of instructions. What we call an electronic computer is one that does that at electronic speeds.
Did the lawyers make this argument fully,
No.
or did
No.
they not
That's the thing.
understand?
No, the lawyers did a very bad job. The Remington lawyers didn't really take this whole line of questioning seriously. They said, that's ridiculous. And as a result, lost that. As I say, the patent was probably invalid for other reasons. And there were other reasons why the patent had to be invalidated, because there was an antitrust suit, and it really couldn't go on the way it was with them extorting money from everybody. So it was the best thing for the industry, once again, to do it. But it was a bad thing for Mauchly, mainly because Iowa just went crazy and they put out these books, and then once people got this had a book to reference, the story took a life of its own. So, all right. So, my point is, Eniac is the coolest machine ever. It was 1,000 times faster than anything else. And that's all that was important. It wasn't that it used tubes. Who cares whether it used bobby pins? It was 1,000 times faster, and it could solve any problem. Imagine if today you could just walk at 3 miles an hour, and the next day, suddenly you could fly at 3,000 miles an hour. I mean, that would be a big change. That's life-changing experience. And that's what this did to the world of computation. And that's why it rightfully had this reputation in its day of being the giant electronic brain. So my goal is to get it back together. It's probably the single most important artifact of technology in the 20th century. And it shouldn't be just scattered all around the world. There should be a big room you can walk into, this big. It's black with blinking lights, and it's huge. And it's the first computer. I want to experience that, because I missed out on that part of it. I don't know if I put up a flashlight on there. Things kept getting smaller. He bought one of these. Go ahead. And finally, he bought a TRS-80. You can't see it too well in here, but you know what TRS-80s look like. There it is. Not just a regular TRS-80. He got the expansion bus, and he's got a couple extra disk drives.
You have one of those over here.
Yeah. He had a line printer, and then he had a letter quality printer. Letter quality printer. Daisy wheel letter quality printer. So there he is. And there's okay. And so there are my parents in the late 70s. Unfortunately, the man died in 1980. He wasn't too old, he was 72. And here's my list of computers that he went through in not chronological order, but sort of in David Letterman's style, the order of what would have been his favorites. If you, because it was really, he was happiest when he had that thing sitting on his desk and it wasn't creating 10 kilowatts of heat at the same time. And he was just able to putter away. He was writing programs for finding prime numbers. He was always doing kind of wacky, ahead of the time scientific stuff. But he really enjoyed just having his computer to himself and nobody trying to timeshare everything. So, as I say, my goal is to get that Eniac back together so we can all have that experience of walking into that big blinking light world. Thank you very much.